everyone, today we're going to talk about energy and its ability to do work. First thing we want to know is that both chemical and physical changes involve changes in energy. And first of all, energy can be either absorbed or released. Energy can be absorbed or released. The other thing is that this is usually in the form of light or heat. So for example, that would be like if you're cooking on the stove, like my husband and children are right now, and they lit the burner and it's making a pot hot to make probably macaroni and cheese or hot dogs, as 5-year-olds love to eat. And you can see under the pot that there is both light and heat coming from the natural gas burning. The natural gas burning is a chemical change, so that's a chemical change. And then there's a physical change going on too. The water is boiling and becoming a gas. The variable that we use to represent heat is the letter Q. We usually see it as lowercase, but it can also be uppercase. And energy, Q, can be transferred as a result of a temperature difference. When energy is transferred, it always goes from the hot thing to the cold thing. You can't transfer cold, you can only transfer hot. So if we transfer something from hot to cold, it would look like this. The heat would be transferred from the object that is hot and has higher energy to the object that is cold and is lower energy. In this case, the hot thing would cool down and the cold thing would warm up. Heat will continue to be transferred until those two objects become the same temperature, and we call that thermal equilibrium. The other thing to keep in mind, though, here is that heat and temperature are not the same thing. I think a good example of the difference between heat and temperature came from Miss Weck. Miss Weck told me if you have a cup of hot water, so let's say the water is boiling at 100 degrees Celsius, and you have a teaspoon of hot water, also at 100 degrees Celsius. They have the same temperature. But then the question is, which one would you want poured in your lap? I mean, neither of them. But if you had to pick one, you'd certainly pick the teaspoon. And that's because while it's the same temperature, it has a whole lot less heat to transfer. Okay, next we can talk about some simple calculations that we can do with energy. The equation that we use is Q equals mc delta T, and those are multiplication signs in between there. So Q equals mc delta T. We already said that Q stands for heat. It has units of joules, which is represented with a capital J. M is mass. We're already familiar with that. We're going to use that with grams. T is another one that we're kind of familiar with. That's going to be temperature, and the delta means change in. So it's actually represented as the final temperature minus the initial temperature. The last value in there is C, and this one's pretty new and is a concept that we want to pay close attention to. C is called the specific heat of a substance, and the units that we use to represent that are joules per gram degrees Celsius. Every substance has its own unique specific heat. It is an intensive physical property of a substance, kind of like density, and you can look it up in a table. The specific heat of water, for example, is 4.18 joules per gram degree Celsius, but that is only for water. For any other substance, you'll have a different specific heat value. For example, in this next problem, we're going to talk about copper, and copper has a specific heat of 0.385 joules per gram degree Celsius. Notice that the specific heat for copper is much lower than that of water. Okay, so let's try this problem together. First, we need to use our new equation, Q equals mc delta T. The problem says how much heat is given off if 387 grams of copper at a temperature of 205 degrees Celsius is cooled to 115 degrees Celsius. We are being asked to calculate Q. So we've already really done the algebra, but we need to plug our numbers in and solve. The first thing I'm doing is substituting T final minus T initial for the delta T. Next, we can plug in all our values. With all our numbers in here, we know that the mass is 387 grams from the problem. We know the specific heat value is 0.385 joules per gram degree Celsius. And then our final temperature we found to be 115 because that's where it cooled to, and our initial temperature was 205 because that's the temperature that it started at. First thing I like to do, just so I don't mess up any of the math on the calculator, is start by doing my subtraction. This gives me negative 90 degrees Celsius. If we want to be technical about sig figs, I should put a decimal there. After multiplying these numbers in my calculator, this is the answer that I get. We're going to have to round it to do sig figs properly, but notice my units are in joules because the grams cancel and the degrees Celsius cancel, so I'm left with joules. With two significant figures, because of this number here, my answer is negative 13,000 joules, and that answers my question, how much heat is given off? Here's our answer, negative 13,000 joules.